All right. So I'm here to present the analytic marching algorithm that uses deep implicit surface networks. All right. So this paper basically begins with talking about the problem of isosurface reconstruction. And essentially what that is that it seems like most of machine learning, you see the concept of like decision boundaries and boundaries of different kinds. In this surface reconstruction, basically the boundary is whatever 3D object you're trying to reconstruct. And there's different ways of converting data about that boundary into a compressed version
Pardon
of.
my interruption, William. Are you going to motivate this with neuroimaging task that you're doing, or should we just like chat in the beginning? I can do it if you want, just where this coming from.
I think you probably have a better idea of what you want to talk about.
Yeah, just to motivate why we're looking at it, and yeah, because like you're kind of jumping into. So basically, we have MRI, which is a cube of gray-valued voxels, and within that cube could be all zeros, or there could be a brain somewhere, or there could be some three-dimensional object. So the goal is to take that MRI and return a 3D model, solid modeling kind, in this polygonal mesh, triangular mesh, and so on. And that list on the screen is how that model could be encoded, how could it be represented. And the difficulty is that we are starting with a cube of finite fixed resolution of some values, but we want to output, ideally we want to output a parametric surface or parametric object, which is infinite resolution. And that's not simple semantics, not just the words. The point is to go beyond the resolution that can be encoded in the voxel space. For example, some of the folds, they collapse into the same voxel, but our result, the mesh or the surface, should go beyond the voxel resolution. And so if there is a fold, it should fold and come out of that voxel, even though the voxel is large. So that's where motivation is coming from. And so one thing is to do this for brain neocortex. But another thing, imagine cerebellum. Cerebellum has lots and lots and lots of small structures that we need to model, and they're way beyond the current MRI resolution. So it would be nice, well, maybe from CT, maybe from MRI, it would be nice to have a method that could take a block, a 3D structure, a 3D rectangle, and return a surface. And so similar task is solved in this paper. I hope it's similar enough to be useful. Okay, sorry about that. Go ahead, Tony.
All right. So essentially, the paper begins talking about the different ways to create that surface. There's a bunch of different ways. Sight and distance function is one of the ways used within this paper. Sight and distance function, basically, the way it specifies this this surface. I need to bring up a pointer. Let's see.
You can see your mouse.
Oh, you can. Okay. So anyway, the sight distance function basically says that things inside the surface, because it's usually a closed surface, things inside the surface are considered negative values, which is kind of an important thing to know about the sight distance function, because in math, distances are not don't have a sign value, but basically negative distance is inside the surface and the positive values are outside the surface. And the reason it's called isosurface is because everywhere along the surface is valued at 0. An isosurface is like is a surface that every value on the surface has the same value. So radial basis functions specify this surface basically with a collection of points that that have like something like a radius associated with them, and then the value of the activation drops off very quickly as you get further away from those points. So essentially the MLP, what this algorithm is doing is it's creating a surface with an MLP, and then it's trying to specify the important points of that MLP. And what an MLP is doing is, if you have a single layer, it'll like basically act like linear regression. But if you have multiple layers, it starts to use multiple hyperplanes in order to specify regions. And as you add layers and neurons, you can specify finer and finer regions until you get, in our problem, you would specify enough neurons to be able to have a mesh that looks like the brain. But at the core, basically, you start with the simplistic MLP and work your way up to that concept. One of the ways that you can specify these surfaces that we might use within our problem is these splines. And splines are basically, it's kind of like the way I saw it explained is like if you take if you're doing linear regression and you're trying to fit a bunch of points, you just have a single line going through these points. Or if you're doing a polynomial fit, you'll have a polynomial going through all these points. But polynomial fits kind of break down when you have a lot of points in a high degree polynomial. It'll like have very large errors near the edges, so you can't really use them. So instead of trying to do these fits that are similar to typical regression, you do these piecewise fits. And the spline basically has some guarantees associated with it that the surface that you use to fit the points will be continuous and smooth, and basically so that you're guaranteed to have like a first derivative and second derivative that is continuous along the entire surface or something like that. So basically the paper doesn't have a particularly graspable high-level description of this problem. So I'm just basically going to be walking through equations, getting to the algorithm. But what the algorithm essentially is doing is that it's walking through these piecewise regions that are created by an MLP and extracting the useful ones, and then finding the points that specify those regions, and and using those to reconstruct the surface. So that's sort of the high level idea. You're basically walking along the piecewise hyperplanes and reconstructing the surface. Only so basically the non-zero activations of the neurons are the values that specify regions that are useful to this algorithm. So first they start off with this this function that basically identifies non-zero activations so that they're not looking at regions that don't have the surface. They use those non-zero regions in order to create a weight matrix. This gets you closer to being able to examine only the hyperplanes that are associated with the surface. So essentially what this equation down here is saying is that this is the MLP. And because it's multiple layers, you have L weights associated with each layer. And the function that the MLP is learning is a sign distance function. So you're going from the r cubed to r, which is the distance. And the loss function essentially is learning the sign distance function, which I'll get to later. So there's a bunch of different properties that they're interested in that they talk about as identifying regions that are near the surface of an MLP. And there's properties that basically say that this is the important piecewise face to look at. And one of the important properties is intersection. So like basically like if you have a piecewise hyperplane, above that hyperplane will be positive and below it'll be negative. So that's why I keep bringing up this the sign distance function concept.
What is the input to that MLP? The whole cube or like small subcubes?
I mean, I don't know if I could like frankly answer that question, but anyway.
I have another question, completely unrelated. Does it matter that this is a ReLU-based MLP? Why can't we use some other activations? You specified that a couple times, and I'm just wondering if I missed something behind that.
Could we use other activations? Yeah, I think that you probably could, but they're using ReLU activations because this whole problem assumes piecewise planar surfaces. I mean, you could probably solve the problem differently, but ReLU results in piecewise linear regions. So
you just arbitrarily make a continuous activation piecewise if you wanted, but
all right. So basically, these you go from the okay, I'm lost. So basically, this H is values along the surface where the isosurface value is 0. They kind of use like doesn't seem to be a whole lot of difference in my mind between H and P. They seem to be closely related, but basically the C is basically like the regions of the MLP that it's carving out. So if you go and look here, like C would be like these regions. H and P are kind of related to the edges associated with the MLP, but and recall this S function basically gives you the activated regions near the surface. Okay, basically theorem 5 basically tells you that if you satisfy all the previous relationships, then you'll be able to march along faces that will give you a surface. So basically you're trying to minimize the sign distance function. I mean, this whole slide is worth talking about, but it's I don't know how to present it concisely. But so but I mean, we've talked about most of these concepts. Z is the isosurface, C is the cells, P are the faces, F is the sign distance function. And basically you need to be aware of all these concepts before you can talk about the algorithm. So basically, once you're able to define the surfaces you want to march along, you need to basically just use like a regular algorithm to march along them and make sure you don't enumerate them more than once. So it's kind of like you have a set, an active set, and where you add faces that you've seen before to that set, or faces that you haven't seen to that set, and basically you push them on as you're enumerating them, and you pop them off as you've identified vertices associated with them that define them. that will help you define your surface. And basically, these A's represent like this function gives you the values of H that you want there, which is a way to specify the surfaces that you march along. And once you march along those faces, you get a series of vertices.
So do they simply assume that somebody gave them the MLP that is trained, or they discuss the training as well?
They discuss the training in like a paragraph. So I actually have like the whole section that talks about their training in here, and it's less than a paragraph as far as I can remember. So like basically, this is section 5, I think, of the paper, and this is the loss function they're minimizing. So you have some ground truth distance, and this is the output of the network. So basically, you're basically training the network to minimize how different those values are. So once you've learned, completely learned what you're supposed to learn, you'll have that the output of the network will essentially give you a distance to the isosurface. And this value is just a regularization term. So this makes it so you have like a smooth gradient within the function that's output. But anyway, so I don't really even know what the input of the network is, I guess. I mean, which is kind of frustrating, but like,
but
I understand what
unclear what the, without the input, it's unclear what the output is. Like, is it in which space it is located? Can it go subvoxel? Can it like just unclear?
Yeah. Yep, I found this paper to be unclear, but that's partially my fault. There's an algorithmic guarantee associated with the algorithm that's useful. Is basically that it guarantees a closed surface mesh. So you don't want to use an algorithm that only works sometimes. So that's probably what makes this algorithm worthy of publishing. Is it provides an algorithmic guarantee, and they have a section on it that gives a proof that I didn't get into. But
okay. Sorry
Okay.
for interrupting. Just a quick question: is this basically like SVD meets, I don't know, neural networks? Like, I mean, this looks like a distance function that you're trying to separate boundaries, but I mean, there's not really a set boundary, but the f(x) minus dx kind of looks like a SVD kind of penalty.
So, I mean, what it looks like to me is that they're basically using an MLP to learn a signed distance function rather than try to do classification. And then once they learn that signed distance function, they can march along the piecewise linear regions that are learned and reconstruct a mesh. I think that's the concise way to describe this algorithm. So I'm going to say that one more time because I think that's right. Basically, like their MLP is learning a signed distance function, and once they learn that signed distance function, they can walk along the zero level parts of the piecewise regions and reconstruct a isosurface for the mesh.
So I can give a comment to that, Amrit, as well. Long time ago, 20 years ago maybe, when first MRIs were there, people would just do thresholding, and that thresholding will give you that distance function, or not a distance function, but actually the surface. And then once you've done once you found the surface, you would apply this cube marching algorithm to convert it into a triangulated surface, where basically you're scanning with a cube and you're looking for binary transitions once you threshold it from 0 to 1, like within the volume, outside the volume. And that's how you would construct the surface of the brain. I had every time, because outside it's the easiest one, the zeros. But then if you apply the mask and everything and extract the brain, then you can do the same again, construct this surface.
Oh, I see. So like this is basically, sort of used with sort of data that you have some sort of surface that you're trying to identify within the data.
Yeah. Like
Okay.
there is that cube that contains zeros and ones or gray level values, and there is an object. One of the next slides, I saw the sofa, right, or something. Yeah, like so you have that voxelized input, and you want to find that object and find its surfaces, and so again represent the surface somehow smooth, like the speculated on the top. That's how a marching cube algorithm, I think, would work. Is that what is
That's called greedy meshing, I think, the top one.
greedy meshing? Oh, marching cubes is the second, MC. Yeah.
Essentially, like all the difference that I saw with those algorithms is that some algorithms are that they create a better surface. They do it in a more compressed way, and then there's time complexity. So that's basically the next algorithm needs to basically be either faster, do a better reconstruction, or something like that.
So I have a couple questions. How does this fare if our mesh has a hole in it? Like if our scanner failed during the scan, we have a big old hole in the brain. Would this still work?
I don't
We're
know.
only doing the closed surface.
Only closed surfaces?
Yeah, the inside hole we also can mesh, but the inside and outside signs will flip, right? We can mesh it as the emptiness will be inside, so it's another. That's my understanding.
Gotcha. And we're assuming that a metric even exists on this thing, right? That the surface isn't like warped in some way.
Well, okay. Let me rewind. So 20 years ago, threshold, get your binary metric, run marching tetrahedrons algorithm. There is a funny story, and extract the surface. Now what they're saying, this binary surface doesn't have to be extracted by thresholding. We can train an MLP to extract the surface from us. And now it's not binary, it's a distance, sign distance function, how close we are to the surface, how far we are. And I assume, I don't know, William, maybe you can comment, that this particular algorithm can take advantage of the sign distance function, so it can curve or smooth the surface better based on the signs. It doesn't have to directly follow the zero iso line. I don't know, iso surface. But is that clear, Brad? Clearer?
Yeah, okay.
Well, the fun stuff about MC and NT, looking at the slide, marching cubes was patented. And I did mention it last time. So people in the whatever sciences community was like, well, that's an obvious algorithm. How can you patent it? Let's change and let's march, instead of scanning with a cube, let's scan with tetrahedron. And they patented tetrahedron for the society, for the community, and everyone was using tetrahedron. The patent must have expired on marching cube.
Well, essentially, I mean, that's the thing that the biggest question I had about this paper is how they talk about MLPs the whole time, but we're using CNNs, which is basically a feature extractor, then an MLP. So I think that basically you can still possibly use this algorithm.
From Turing completeness, they're equivalent, I think. Neither one of them is Turing complete. I mean, they're just functions. They're function approximators. Or what do you mean? How it is different?
That's my question. Is I don't know how different it'll be, because the feature extractor maps the input space into a lower dimensional, like latent space. So it's just and then you're doing whatever you were doing with the MLP on this latent space. I don't know. I think they'll be equivalent. I actually think the CNN method will be more efficient than theirs, but
yeah, it will be more efficient, but at the same time, I don't see how they do this higher resolution. What we're interested in MRIs we are getting the cubes, the ones on the top. Like that's our input. How can we go beyond that resolution and possibly unboundedly beyond? Like we want a little better resolution. Okay, here's a surface with better resolution. We want more and more and more. Just do more subdivisions and smooth the surface. That's how usually we do the thing. So I wonder how this method copes with it. Does it do it by MLP, or MLP returns just a rough within the same surface, within the same space of MRI cube, rough subdivision, and then their algorithm smoothes that subdivision? I wonder this transition, how it is done.
Just as a quick thing, in their implementation details for their experiment, they say that they sample 100 points from 3D mesh models that are normalized to -1 space. So I guess that they take the points into the MLP. That's why they use an MLP, I guess, because they just have sort of 3D points, and that's how they try to reconstruct it again. So I think that's also why they use an MLP here instead of a convolutional neural network, because you have, if you randomly sample them, the distance between them doesn't have to be like a normalized distance like in a convolutional.
So they're not.
Yeah, so it's easy for them to calculate the distance for their experiment.
Okay, that answers my question as well, actually.
Yeah, so I think what they sort of do is they have these like here, the ground truth mesh, they sample 100 points and they try to reconstruct the original surface using sort of a roughly sampled same mesh, and then they sort of, to me that's what they, but I also, it was super hard to read. I don't know what this is just from the implementation details, but yeah.
So I still have to wonder if this connectedness assumption is going to get us into trouble with MRI, because we have brains that have like weird folds and pinches in them, right? So you're going to get something that's, especially when you look at the continuous mesh, the ground truth, it's going to be really hard to treat as a connected mesh.
Oh, it is. Each hemisphere is a sphere. It's a genus 0 object.
Really? That's weird.
Yeah. There are no, it's like a napkin that has folds, but it's also just, basically what FreeSurfer does, what is it, cuts the corpus callosum, or cuts that bridge, but even if you don't cut it, it's still a sphere. You can represent it as a sphere.
It's just a transformed napkin, right? Yeah, okay.
Well, I think about it as a balloon which you kind of pop, and it kind of shrink wraps the brain and just gets the folds.
Interesting. All right.
But it's very intricate, and it can have very weird folds, but it can't touch. Especially, there is another catch there, because for finite elements and boundary elements modeling, we want to use that mesh that we get from the brain for all sorts of numerical modeling. And there you cannot have self-intersections, or even the surface touching itself, or the two surfaces, say the PL, like the internal boundary between white matter and gray matter, and external boundary between gray matter and CSF. They cannot touch. If they touch, it's a singularity in all of our solvers, and they break.
Right.
So you need resolution higher than the one that kind of leads to touching, and adaptive meshing would be the best, I think. Otherwise, we'll be wasting a lot of time. So at the places where they get too close together, we want more triangles if we're doing it with a triangle. And the rest we don't want to waste. Like currently, I don't think, from what I see, how FreeSurfer does it, the output, that it's uniform mesh. That's why it has, well, another difficulty. Our cube is, say, 64 cube or 256 cube at best, but each hemisphere is around 300,000 points. So, and it's only surface, only the surface of one of the whatever subdivisions, and so it's a huge space. We're starting with a rough resolution space, and we want practically infinite resolution. It would be nice to get non-uniform rational beta splines or something representation where it's like infinitely smooth, Well, William will get us that soon. It's actually, we're working on a project trying to solve a problem with other approaches, and William is exploring different ways, and that paper was along the line.
Yeah, the only thing that came to mind, the only idea that this really sparked for me, and it's probably not well formed, but the main difference that I've seen between what we've been doing for this problem and what people normally get taught about neural networks is that neural networks usually get taught for classification. And instead of like trying to do logistic regression, we're trying to predict like real values and do like basically regression in a very complex space. And like splines are a bunch, I mean, there's a bunch of different ways to fit that surface. And we're trying to use a neural network to recreate that surface. But I think one of the most valuable things in deep learning is not so much RNNs, CNNs, MLPs, or anything like that. It's actually backprop. And I think that if you could specify splines, like if you have a set of points that define splines and a set of functions that define those splines, and you can get a ground truth distance of some kind, and you can like basically do backprop on like this equation. You can specify like a bunch of different ways of learning that surface that don't involve neural networks. As long you're just basically trying to minimize a distance between what your surface guess is and what the actual surface is. So
you do have spline nets. I don't know if that's like the same idea, but I've seen like a few. I don't know how many there are, but there's like this idea of spline nets, which I think is
yeah. I mean that's exactly kind of what I'm talking about, because I saw some stuff like RBF networks, and there's just a bunch of different ways that you can learn a boundary, and that's basically what neural networks are doing. They're doing it with ReLU. They're doing it in a piecewise linear way. CNNs first map whatever you're doing into a different space before they do that.
I only 50% partially agree with you, if I heard you correctly. So basically, you're a fan of differentiable programming. So you're saying deep learning is nothing but differentiable programming. I would, if I interpreted what you just said correctly, right? And
I mean, I guess that's essentially what I'm saying.
yeah, I would say deep learning is nothing but differentiable programming plus architectures.
Yeah.
So that way, CNNs and RNNs, they are important, because you can't just like, well, first of all, because of recent results, take an untrained CNN, and it will be a very good predictor for your images, because its architecture is an inductive bias for images from the start, just the architecture, translation, and everything. The same for RNN. And like when you look at your problem, at least the problems I've solved in practice, not just for papers, if you think about your problem and you can encode the inductive biases of your problem into the architecture, then you can learn it much more efficiently, and using differentiable programming, yes. And yeah, Harsh is there. Yeah, Node neurology is nothing but differential programming, like completely.
Okay.
One quick question on top of all this. With FreeSurfer, they have a set amount of edges and faces, like 32K mesh or whatever. And I mean, you have so many different brains with so many different folds or whatever. How do they, decide that we can just use? Because I feel like if I use this algorithm, it would just come up with however many faces there are, right? If I understood it correctly or something. But like, I was wondering how they like limit it to like downsample or.
I don't know the internals of how they actually do it, but I can try to reconstruct the way I would do it naively, and we've tried that too. When I was working on similar problems 20 years ago at Los Alamos National Lab, my goal was if we take a sphere, how do I place the points uniformly on the sphere such that my spherical triangulation is as uniform as possible. The Los Alamos guys were laughing at me. They're like, this is top secret because that's those algorithms that do that, because for the atomic bomb and for the hydrogen bomb, to simulate it, you need the most uniform coverage and stuff. But it was kind of a running joke. But the point is, if you take icosahedron, I'm not pronouncing it right, icosahedron, and you start subdividing it and just pushing the dots and subdivision out to the sphere and keep doing it, you get sort of a uniform sphere without any knowledge about any brain. So you get a sphere with uniform triangulation. And then you just feed that same triangulation to all of the brains. And that's how you can keep exactly the same number of facets, exactly the same number of triangles. I think they're doing something like that. Like they have a sphere with already pre-triangulated and then just moving the points around. We can ask them.
Yeah, I mean, I guess that also allows you to do, I mean, the crazy registration, right? I mean, if you have the same amount of points and the same amount of spheres, you can find that nonlinear transform pretty fast, I'm sure.
Yeah, but the points don't, like, for free surfer purposes, gray matter volumes and things like that, it doesn't really matter if they're the same or not. It's just how you compute the values with them. Probably it's easier to register, but at the same time, they don't have to be the same.
I have a question. So I'm out of presentation mode and just trying to understand this paper better using y'all's knowledge. Like, did anyone figure out why they are multiplying the weights? Like this in particular confused me why they were doing this. So.
Well, you're switching too fast. I can't even read what's on there.
Sorry. I didn't think there was enough context to learn from there.
They're saying they are multiplying through all of the matrices. Is it an element-wise, or it's a linear algebra multiplication?
Yeah, that was basically what I figured. I figured it's probably not element-wise, but I don't. I mean, that's what that notation means, though, doesn't it? That's just like scalar multiplication right there.
No, notation can mean anything. Notation, you define the meaning of notation. It's
okay.
Yeah, whatever they meant by it. But what I see is, yes, you can take an MLP and multiply everything through, dropping nonlinearities. If you assume that nothing is negative as the result, then ReLUs are giving you just that, just a linear transform. So probably they're assuming that. I don't know. If all of your nonlinearities are ReLUs and there is nothing in negative, so there is no thresholding, you're just multiplying through and you get a single matrix. That's a guess. Number 7, yeah, let me look in the paper. So what is R there?
I know that R with the little R tilde means something that has intersection and non-intersection properties. It's like an area value near the isosurface, but I don't remember.
What is W superscripted by R? That's what I'm like. Is it a single value, or what does that R do to the matrix?
R is a linear region in the input space. So you can partition the input space into a set of R, like big R linear regions, and any region in R is small r. That's what they're saying. I'm just reading from the paper.
Yeah. I'm trying to find that too. Yeah, like right above equation 7, they started with a proper sort of definition of the MLP, but then they added this W sub F. They have MLP's outputs, but then they collapse it to a single number. Well, that's the output of the network. Mhm.
What I also thought was a bit confusing. I didn't get through all of it because it was very quickly like lost sort of concentration to read through all of the like mathematics, but how they sort of have these hyperplanes, and then so they say that like every neuron in the MLP has like a hyperplane, right? That's like one part of it. How they get to like an analytic surface, right? Because it's still piecewise. And how do you sort of get to the final? I don't know.
Yeah, I thought that's their contribution, that MLP with ReLUs partitions the space, the whole input space, into sort of flat, piecewise linear regions. And
I mean, that people kind of already knew that though. So it was like they just applied it to assign distance function rather than anything like classification or something. Like if you look in like neural network security, they talk about piecewise linearity of neural networks like all the time because there's a lot of ways that breaks. And there's other things that are weird about neural networks that they kind of mention in this paper. Like there will be some of these analytic faces and analytic cells will open towards infinity, and you can actually exploit that for adversarial attacks against neural networks by like crafting a point that's somewhere along that infinity, but nowhere near where your training set expected it to be. But
yeah, but nevertheless, so MLPs with ReLU network, with ReLU nonlinearity, partition the space, input space, into piecewise linear cells. And the contribution of this paper is to smooth those cells, to use them, like to create a surface from this rough kind of a honeycomb structure. That's what I understand. But it doesn't look like we are able to figure out how they do that, right? Or why is it interesting? They kind of obscured a lot of things rather than making them clear.
Yeah, we in my deep learning classes at my university, we used to call this mathiness. Like they just obscure every sort of idea you can have about this by just putting a lot of math equations in it, so everybody thinks it's super interesting. Although maybe on like an abstract level, like how what it actually does, it sort of is pretty trivial, but it just seems super complex by how they just use all these. I mean, it's cool that they prove it. I mean, definitely kudos to proving it. But I'm just wondering how sort of groundbreaking the main idea is. Like you said, if you're
my postdoc advisor called this sigma shock. Like, oh, too many sigmas. I'm like, I can't understand. It's so painful.
yeah, I'm guessing that's a lot to get past reviewers. I mean, if you have a simple idea that you want to get out and they reject it, you probably have to add a bunch of mathiness.
No, your idea has to be elegant and robust. But okay, yeah. The last one that Alex posted, where people cheat about the amazing figure about self-supervised learning, according to publication, how the performance improves, and according to evaluation with years, nothing changed. And I tagged you, Eloy, I tagged you in a random channel. Just what you're talking about, exactly that. I will post it in the reading group again. But maybe not. We don't know, right? But the authors clearly didn't do effort, like didn't make enough effort to explain this the significance besides like, oh, go through the math and you will understand. That is your perception, William. You probably the one.
Well, yeah, of course that's my perception, but yeah, I figured that y'all wouldn't have similar problems. I figured that was a noob kind of thing. But it's good to hear that y'all kind of feel the same way.
Honestly, I started reading this. So for me, it's evening, and I started reading this at like I think 3 or 4 p.m., which is 2 hours before this meeting. And you know, I was like through the second page, and I was at like Colliery 2, and I was like, you know, I hope William sort of knows what they're talking about, and then I can just sit back and listen, because this is, you know, it's been a long week, and it's like Friday mid afternoon. I just, you know, I'll just wait for the presentation.
Nah, this paper I might have been able to parse if I had been working in, if I had known what polygonal meshes, triangle meshes, sign distance functions, radial basis functions, etc. Like if I'd been working in this domain, I might have made a lot more sense of this. But this paper was painful. I had to kind of go out and basically watch a lot of YouTube videos about what the heck this stuff is, and like
that's good.
And I learned things, but unfortunately, I know that I didn't do a good job of instruction. But I think a little bit of that is the paper for sure.
So, but the goal is still there, right? So interestingly, I haven't seen any papers that talk precisely about that, our problem, 3D, like 3D cube, MRI, like converted into a mesh, which is infinite dimensional for any practical purposes. The problem of segmentation is solved originally by UNet, and then Alex solved it by MeshNet a little more efficiently. But the thing there is we go from the same space to the same space. The output space resolution is the same as the input space resolution. We just assign a label to each voxel, and that's solved now. And even free surfer developers are completely bought into that approach. They just published the paper called Fast Surfer, and well, it uses UNet, losers. But anyways, the surfaces themselves, and I just accidentally I spoke to Bruce Fischel yesterday about that. I've asked him if they've been working on it, if they've tried any kind of surface reconstruction, and he said that yeah, that nothing conclusive. They couldn't get any good solution with deep learning yet. So that's interesting that this problem is there and it's still hard. So I think that's why this problem is much more, suddenly from yesterday's conversation, it gained more points that we should do it. It's a difficult, challenging problem, and yeah, that's. But so for next, thank you, William, for trying and suffering through the paper and leading us through.
And thank you for suffering through this presentation.
Okay. So for next meeting, Riyasad has been working on this interesting idea for quite a while right now, and it comes from sparsity regularization, originally inspired by non-negative matrix factorization, for at least for me, where by adding non-negativity constraint, we suddenly start getting sparse results. And then, as you know, ICA which our group, the whole group in trends is working on one way or another, is also tends to give sparse solutions. So the question there in the paper and the research that Riyasat is working on is, can we solve two problems? One problem is, instead of fiddling with a hyperparameter on regularization, Lagrangian style, you know how usually we add sparsity even to deep learning. We have a model, we have model's likelihood, which we want to maximize, and then we add a lambda times L1 norm. Of course, we want L0 norm, but it's NP hard, so we do L1 norm or L2 norm. Well, L2 actually doesn't do the sparsity, L2 distributes the energy equivalently. So L1 norm, yeah, okay, lambda L1 norm. Now, if we want sparsity of 30%, we just have to spend 30 million hours in front of computer and fiddle the lambda and run multiple times, and we're good and happy. But then you go to a new data set and like, oh, wait a second, now spend another 30 million hours and find a new value of lambda that corresponds to the desired value of sparsity. So thanks to Patrick Hoyer from Ireland, and I don't know where he's at right now. So he came up with a measure that transfers between data sets. If you set it 0.5, it will be 0.5, and it will mean 50% sparse. But another question arises is, can you in one optimization still arrive, like you set it to 30% sparse or 90% sparse, can you optimize and get a solution? So Riyasat is working on a solution that is called groups sparse projection, GSP.
Yeah.
Yeah, and that does it. That does exactly that with some extra overhead. But it would be good, I think, if Riyasat goes over it in details. In detail, like we have all theory worked out with collaborators and even some exciting experiments. Maybe by next Friday we can have transformer, right?
Yeah. Yeah, maybe, yeah. Yeah.
Yeah, so why don't we talk, the paper is unpublished. We tried a couple of times, got rejected for no reason. Some inferior papers get accepted. So I suggest that paper. It's on arXiv, so all of you can read that, and maybe you can tell us what's the problem. But I think it's an interesting concept, and it is also a little bit sigma shocky, thanks to our collaborator who's done the theory of the paper. But we will explain everything to the details what is happening. So so if you don't mind, let's do that next week. I'll post everything online, and I'm stopping the recording.